Good. All right, guys. So we are going to get started, right? So we have our labs from Kmeans to cover, and also I want to cover a new section today as well. So let's get started. Here's my screen. All right, that should be visible. All right, guys. So in the this week, we started looking at unsupervised, right? Kind of a algorithm summary where we are. We spent quite a bit of time looking at this, supervised learning, regression algorithms, classification algorithms, decision trees, right? And then now we made a switch to do unsupervised. So last week we looked at clustering algorithms, mainly K-means is very popular, and there are other clustering algorithms as well. But once you know one, you should be able to adapt any of them very easily. So for the K-means, yeah. So right. So we go to the guide. Right. So we have a new section on supervised algorithm clustering, K-means, right? So K-means, I gave you some reading, and also labs. So I have 3 labs. Let me run through them all real quick. So first one is using synthetic data, and then the other one is cost data set, and the other one is Uber trips. So they're gonna build on each other's difficulty. So let me look at the. I'll just do it on my local machine. So here again, you guys have the link right here, right? These labs in our guide, right? Which you guys know already. Okay, so exercise 1, 2, and 3. So I'm going to zip through them real quick. And also I made the class submission folders open, right? So you can look at other people's solution as well. All right. So also intro one, kind of very simple, very quickly. Let me kind of clear all the outputs. All right. So the idea is, remember all of algorithms, we always kind of started with like some random data, right? And then kind of, just to get the algorithm, get familiar with the algorithm, right? So that's what I want to do here. So I'm doing make blobs. So this is nothing new. You guys have been doing this, for a while now, right? So basically I'm saying, create me a blob with, how many centers? 3 centers, right? And then we plot the data, right? So we get it, right? 3 distinct clusters. And they are color coded, and everything is nice. So there's nothing new here, right? Just something we do. And this is something I've been kind of promoting a lot, because sometimes when you want to test an algorithm, just wants to get some data quickly. And this make, the make blobs, make classification, these are really great, right? So please, don't discount them, use those, right? So all right, so that's our data. So remember, we have 3 clusters, right? You can see here 3 distinct clusters. All right, so now I want to run K-means on this one. So here's my K-means, right? Importing K-means. Sharing my screen. Yes. Okay. Importing my K-means. 1 second. Let me bring up the chat window as well. All right. Now, so K-means. Remember, think about K-means. K-means cannot tell me how many ideal clusters there are, right? So it'll basically go find clusters whenever whatever I tell it to, right? So we know we're looking at this, this data. We see 3 distinct clusters, but I want to kind of get you guys started with, let's say if you do it like K-means -1, right? So let's say we have 3 clusters. I tell K-mean go find, say, like 2 clusters, right? So I'm going to do like a -1 +1, like one lower, 1 higher, and then we'll do the exact one. So I say, okay, K is this number of clusters -1, which is 2 basically in our sense, right? And I simply say that's it. K means number of clusters K, meaning go find me 2 clusters, right? We fit, actually let me make it a little larger so you guys can see better, right? So we fit the data, right? Again, so Remember, there's no training and testing. We give the entire data, right? We give the entire X. There's no X train, Y train anymore, because why these are unsupervised algorithm, they are going to go look at the patterns in the entire data, right? So fit, that's it. Again, all of the, right? All of this is pretty straightforward, right? So, right, so K means fit, right? And then I'm sort of predicting, right? So what I'm predicting is basically, I'm saving it on Y pred. So let me show you guys how it looks like. So remember, we had two clusters, right? Because number of centers is 3, so I said K equal 2. So basically, my cluster number is 0 and 1 because we are only two clusters, right? And they, you can see their points are randomly being assigned, zeros and ones, right? This is not a binary classification, right? So sometimes people get confused. These are cluster numbers. Since we are two clusters, just zeros and ones. That's it, right? And as the increased number of clusters, you will see, we can start 0, 1, 2, 3, and all. Okay. So that's K-means. So okay, let's see how the results looks like. Okay. Interesting, right? So, and this is why I love this, matplot with the color coding, because remember we had 3 clusters. This is the original data, and I told K-means find me 2, right? Because and K-means dutifully goes and finds 2 clusters. Look at the color coding. See how it's kind of finding out, right? So there we go. Right, so one cluster, so the center should be somewhere around here. I could upload to the center as well, but you guys get the idea, right? Put the center here, right? So one cluster, look at the color coding, and another cluster here. So what it does is, even though there are 3 distinct clusters, I'm kind of grouping into 2. So it says, oh yeah, I'm going to group these 2 because they are kind of close together into 1, and then another one here. Interesting, right? So when you do color coding, it's pretty obvious where the right, how the clusters are being centered. Right? Pretty cool. Does that make sense, guys? Right? We just cluster some random data, and I did right, 2 clusters. All right. So same thing. Now let's do let's do one more. Right. So remember, I have 3 centers originally. I'm asking K-means to go find me 4 clusters in the same data. So let's see. All right. Run K-means again. So again, look at this, right? So randomly assigned. So this is 0, 1, 2, 3. Because cluster number starts at 0, right? So since we are doing 4 clusters, we have 0, 1, 2, 3, and you can see they are randomly assigned. All right, let's plot this. There we go. See the cluster, right? So these 2 it kind of keeping whole, and then this one kind of finds 2. So you guys get the idea, right? You can ask K-means to go find any number of clusters. Let's say I'm just say just say find it. You can just play around with this, all right? You start seeing, right, how K-means starts clustering. Right? But the actual clustering is going to be right. So when you really want to do is, you want to say actual clustering is, you want to find the number of clusters, right? When you do that, and when you plot this, then K-means output matches the actual output, right? So it's kind of a fun way to look at K-means and right, how it kind of just clusters. Any questions on this one, guys? Does it give you an idea? Again, because the actual K-means is very straightforward, right? That's it. Just 2 lines of code, as you guys come to know by now. Yep. And then I think there's like a K-means inertia, I think. Yeah. All right. So this is our error metric, right? So for example, right? So if you did so if it, for example, let's say K-means say so let's say -1, right? And then I do the inertia here, right? It's like 17,000 something, right? So can I keep a note of this, right? So K equal 2, right? It's like 17,000 something. Okay. And then when K equal 3, you will see here, right? Then it should drop down pretty quickly, right? Because that's it, that And inertia here, see 1900. You can sort of see here how it dropped, right? So K3 is this guy, 197, right? So you can sort of see here, and this is kind of confirming, yes, right? And remember, as we keep going, right? For example, let's say, let's say if I set K equal 4, Lambda does +1, right? So let's see what that does. So you can say, right, it's kind of further dividing, and what's the inertia? 1600. So you can sort of see right away, right? If I kind of plot this, right? I should have done this probably, like 1685. Yeah. So you can see here, I mean, the initial drop is like from here, right? K equal 2 to 3, big drop. So you kind of envision the graph, right? Kind of like imagine like virtual graph kind of going like this, right? Like this is K, this is WSSC. I think 3SS, WSSC, right? So it's going to be like this, big drop, kind of tapering over, right? So this is K equal 2, right? 3 is here, 4 is here. You can see it in, right? So since 3 is a good number, then after errors are pretty, right? Pretty flat. And this is available region. Okay, and that's how we sort of try to figure out what's the best K is. Yeah. Good, guys. Does that make sense? Excellent. All right, let me pause here for a second. Any questions on this one? Right? Do we understand the basic mechanics? Right? So idea is, right? Take some data, vectorize it, and that's why make blobs is great, because all the work is done for us. And then basically give the entire data to Kmeans, and then we have to tell how many clusters to find. And Kmeans will go dutifully find, right, all the clusters we want. So good. What else I want to highlight here? All right, guys. Good. Good question. So question was, how do we know the which column we are clustering, right? Exactly. So here I'm clustering on all columns because remember, because I'm feeding my entire X, right? So yeah, it's kind of using all the columns. And here's easy because because we know all the numbers, and I think I only have two feet, like two columns, right? X1 and X0 and X1, right? The next one, we are going to choose the columns to cluster by. Exactly. Yeah. So that's a good question, because sure, we understand clustering, but using what attributes, right? That makes a big difference. So let's do the next one, which is basically the empty cast data, right? So here, what we are going to do, we are going to actually select the columns we are going to use. All right. So again, you guys have access to all the notebooks here, right? They're part of the I put them in the book guide, right? You can grab those, and I'll also upload these at the end of the class into a Google Drive, so you can find it that way. Either way is fine. So since Kmeans is a little new, right? Because you guys are pretty good at classification and regressions by now, because you've done a few of those. So since Kmeans is new, I'm gonna giving you guys a notebook with most of the right, most of the work is done. So because the kind of a new way of running the algorithm. Okay, so let me walk through this one again. This is Kmeans 2, right? Empty cast. So we are going to select some cast data and select and cluster. All right. So that's my data set. So open the data, so you can see the data set, right? So it's pretty. So one of the things I kind of started doing, and this is something I think is worth mentioning. All right. So I use a printout data set like this, I should say data set, and when I do this, it typically prints out the first few columns. The first few rows, right? 10 or 20 rows. Now I started doing a sample, because what I found is sometimes when you print like this, when you just print like the look at the index number 0, 1, 2, 3, right? You're printing like the first few rows, right? If we have like sometimes skewed data, sometimes the data tend to skew on the top or the bottom, right? And so when you look at the data, you may not see the full picture. So when I do sample, so here, I'm doing like a sample, sample 10. Look at these numbers, right? See, right now the numbers are ordered, like, it's putting each, first 10 columns or whatever. But when I do sample, you will see this now, the column number, the row numbers change, right? It's randomly sample. So I kind of started doing this a little bit more because it gives you like a good, right? Basically you're sampling data. You're not just looking at the top 10 rows or something, right? So anyway, so something I sort of started doing myself lately. Anywho, so if you look at the data, right? So here's the data, right? So car model name, and all the attributes for the cars, right? So it's just typical stuff like MPG, cylinders, horsepower, and all the usual, right? So now here I'm only going to select 2 attributes, MPG and cylinder. We could have used all of them, right? But here for simplicity, I just want to use just 2 attributes, number of miles per gallon and the number of cylinders. And let's cluster the cars with that. Yeah. So, all right. So here, right? Here I'm creating another data set 2. Just just selecting these three columns. I'm also selecting model just because when I print it out, I want to see what the what the car name is, right? That's it. So, but my X is now, what's my X? My X is just MPG and cylinder. That's it. All right. So select the X. There's no Y, right? Because we're not doing a supervised, right? So just X, just input data. That's it. There's no predicted data, right? So that's it. That's my X. So you can see, right? My X is MPG and cylinder. That's it. So these are my vectors. And so let's let's do K-means. Again, you get some K-means here. So I'm going to say start 2 clusters. And I put the random state just so we can all compare results. You guys know by now this is optional, right? So I just left this in just so when you run K-means, we all get the same errors and whatnot. Right? That's it. So that's my K-means, right? With 2 clusters, fit the entire X, right? And that's my model. You can see, right? So K-means is done. My WSC for K2, you can see, is 416. So for 2 clusters, my error is 416. All right. So let's, and also you can sort of look at the, right? You can sort of inspect the things a little bit, right? So remember, these are the predictions, right? So remember, since we have 2 clusters, cluster numbers are 0 and 1, right? And then you can sort of right? You can see, you can yeah. Okay, so I kind of need to. So this is how the labels are assigned. So you can see. Let me see. About. Oh, okay, yeah, fine. So some APS have changed, so that's fine. So each data is assigning a cluster. You can see, right? So this is not prediction like a binary prediction. Again, I keep saying this, right? Because you understand this. This is just a cluster number. So this data belongs in cluster number 0. This is in cluster number 1, so on and so forth. Okay. So let's sort this data by our cluster. Do I have? Yeah. So let's look at the data, right? So here's my initial. So I'm sorting by cluster first, then I'm sorting by MP just for right. It look clean. So cluster number 0 is here. Everything here is cluster number 0, right up to here. And you can see, right? So you can see the first few cars, right? You can see here, right? These are like low mileage cars, starting at 10 miles, right? And then kind of going up to what, like 19, like 21 something, right? And they're mostly 8 cylinders, and there's some 6 cylinders, and there's some 4 cylinders too. So again, the grouping is not exactly perfect, right? But it's what it is. And the other group, again, group number 1, right? This guy, last column number 1 is these guys. Okay. And here you can see this is very uniform now, right? These are high mileage cars, like 20 to 30, and mostly 4 cylinders. The previous group was not that great, right? Because it's kind of mixed. So we see there's still room for improvement, but this group looks pretty uniform now. That's very good. Okay, so that's K2, right? So for K2, did you get WSC here? Yeah, so K2 WSC like 416, right? So Now you're going to increase the K a little bit more. So I say, K3. Okay. And then, right? And then print out the inertia. 169, you can see it's dropped pretty well, right? Again, same thing. Let's do clusters, right? So now remember, now we have three clusters, right? 0, 1, 2. So let's look at the cluster number 0. These guys. No, just these guys. Okay. All right, let's look at these guys. All like low mileage cars, 10s and 15s. Number cylinders now 8. See, now this is a little bit further refined, right? So now these are all 8-cylinder cars with low mileage. Good, good. Let's do the next group, right? Again, I'm looking for like 1, right? All the ones. Let's look at all the ones here. Let's see. This is good. This is pretty much like before, right? All the high mileage cars with 4 cylinders, right? That's 1. So 0 and 1 looks pretty uniform to me, right? And then 2 is a little mixed, right? So look at group 2. These guys. So it's a bit, bit of a, like they're like mileage wise, like high teens to like low 20s maybe, right? Basically centered around 20 plus or minus, right? That's a mileage. But look at the number of cylinders, like 6, 8, 4. It's kind of still mixed. So these can be still refined. But one thing you should see is like the pattern has started forming already, right? You can sort of see here. Yes, this group is a little better than what we did before. Okay, so rather than kind of do things manually, and again, we did the K thing manually, right? We just increased the K, right, from 2 to 3, and then look at the data. So what we are going to do, we're going to do this in a loop, right? So I say, okay, right, do a loop 2 to 32, right? And then so I'm changing the K from 2 to 32, right? And running Kmeans. So for I'm changing the K for every loop, and then you're printing out the WSC. Right. So let's see how that looks like. So you can see here, right? As K increases, the WSC drops pretty sharply, and then as the K is approaching like sort of 30, right? You sort of see here, right? My error is pretty much 0. Right. So let me plot this here. You'll sort of see this. Right. See, it drops pretty sharply around like 5, 6 maybe around here, and then and then it kind of flattens out, right? So and then you will see, right? The reason it's complaining about 0 is basically it says, right? So you say, look, as you're approaching the number of, we only have 32 data points, right? So as you're approaching 32, it kind of says, hey, you're kind of clustering, right? Error 0. It kind of says, look, you're kind of clustering the number of data into itself. So you're not really clustering, right? Because now each individual point is its own cluster. Right? So and it's kind of giving out a warning and say, hey, right? Yeah. But in real life, we never like imagine, we're not going to have 32 data points, right? We will have, probably like thousands or millions of data points. So we will never go up to the actual number, but it's kind of a good sanity check, right? So the K-means is warning, hey, you're kind of clustering everything onto itself, basically. Right? So looking at this, what do you guys think? Like, so again, you can see again, and this is a typical K-means, it'll drop down sharply. And, so it's sort of maybe, what's the number of clusters? Maybe like, somewhere around here, maybe, right? To me, maybe, 6 or, 5 or 6 around there, right? So it's a reasonable good K-means. Again, so here what we can do is we can sort of, experiment with these values and then figure out what works for us. And remember, we talked about this, last week, right? Because there's no like a right value. So nobody can say, oh, right K is 6. It's somewhere here, right? And that's what WSS is telling you. This is the WSS in a graph. So now you need to bring in other factors to basically, choose your K, right? So not this just gives you like a little range. And then from here on also, you can include other metrics. Like for example, let's say this is customer data. And maybe you can bring in other factors like, amount of money they spend or something, what I mean? Like, something else you guys want to, right? You want to bring in and then say, okay, maybe, if you group them into 5 groups, our metrics make sense, right? So that's why these are a little fuzzy, right? So, and now you can sort of see the difference as well, because compared to the supervised learning, where you get like a number, like what's the accuracy, you'll tell me, you can tell me like it's 72.7, right? Whatever, there's a number. But here it's a little fuzzy. So hopefully that made sense. Right? Good, guys. So any question on this one? Let me look at the chat window real quick, and please ask away any questions. Right. So here, what are we highlighting is simple data, but I'm telling you guys, how do you're selecting which columns to cluster by. And another reason I pick the cars data is twofold. One, we understand cars, right? We can get, when I see the result, I can see, oh yeah, right. I can see MPG cylinders, and I can understand. And number two, they're all numbers, right? Meaning we don't have to vectorize them, which is great, right? Otherwise, you have to go and encode them and all this. And you guys have done this, right? You guys know how to encode categorical into numbers. But yeah, right. But having just numbers to start with is nice. That's it. All right, let me see the questions here, guys, real quick. Right, so we showing you guys, how to choose the column, right? Basically, what you do is you select the X. Remember, whether you're using unsupervised or supervised, always select the X. In supervised, we selected the X and Y, remember? Because, supervised had, input and output. But here we only have input because, right? We are doing clustering. Let's see. Let's see questions. Right. So kind of the question Umesh, I'm kind of paraphrasing. Is it possible to merge clusters, right? That's kind of what I'm guessing you're asking. Yes, you can, right? Because remember, when you're doing multiple iterations, right? Remember the previous one, we started plotting the data, right? And when you start plotting the data, sometimes you'll find patterns. You say, what, yeah, we want to merge this data with something else, right? So you can definitely, use this. But in K-means, one thing you will make sure is K-means is what we call hard clustering. What I mean by that is one data point can only belong to one cluster. Like for example here, right? This is a good example. Like one data point will be either I'm guessing purple or yellow. That's it. It cannot be like in between, right? So K-means, and this is a property of K-means, it's called hard clustering. Membership is only one, meaning one data point only belongs in one cluster, right? There are other clustering algorithms that allow for fuzzy clustering. So like, a data point can belong to more than one cluster. So you can say, okay, I have a data point that's kind of 70%, purple and 30% yellow, right? You can kind of like this, but not in K-means. K-means is basically a hard clustering. It's either, here or, not here. That's it, right? So look at it, like, for example, things like, some of the topic modeling algorithms will allow for fuzzy clustering, right? So that's going to be on this, but anyway, just to kind of give you a sense, right? Just so you understand, K-means they can only belong in one cluster.
Like, for example, like you have a clinical research going on two different organizations. And if I want to see the similarity between these two research, so do I need to merge the data from these two organizations and see it? So that's what I was looking at. For
Good question. Are they kind of doing the same data? Like, is the data same?
Yeah, data can be a little different, but they are doing the same research. For example, COVID-19 research going on.
Right. Interesting. Yeah. So I'm guessing let's kind of, if I'm assuming that if the data is same, right? Like for example, just to kind of keep things simple, right? But then if the data is same, then one thing they might differ is maybe, which attributes they're considering, right? If you remember, so let's say both teams are looking at the same data, but each team maybe chose different attributes to cluster by. So let's say, I chose MPG and cylinder, but let's say another team chose MPG, cylinder, and horsepower, right? So now the input vector is different. So can you merge the results? It's a little complicated. You understand what I'm getting at, right? Because now because the criteria Kmeans considers is now different. Yeah. So I don't want to say yes, but I don't want to say no either, because now we're changing the data, because even though it's the same data, right? But the data K-means looks at, it's going to be different, right? Because here, right, you're changing the vector.
Yeah, because confidential sake of one organization may not share the data. They may give the patterns. So can I able to
Right.
derive a new pattern based on the whatever patterns?
Yep. Actually, that's a great question. And this is exactly what we are going to cover today. So in the PCS section. So let me do that, and then we'll come back to the question. I think that's a great question.
Sure.
Yeah. Very good question. Good, guys. Let's see, where are we here? Yeah, so in K-means perfect clustering is like, basically at this point your inertia is 0, right? And that's why, remember it was kind of get warning and say, hey, you're kind of clustering. As you can see, as K is approaching, 32, you can see the error is kind of almost 0, right? Kind of, 0, 0, 0. And then that's why it's complaining and say, hey, right? You're not really clustering anymore. You're kind of assigning individual points. Yes. So inertia will be 0 if you consider perfect clustering. So what is perfect clustering? That means like, each data point is on its own cluster. Right? So technically correct, practically not very useful. Right? So yeah. So yeah, so how do you solve the fuzziness, right? That's a great question. And so there's not like a right or wrong answer because this is inherent in unsupervised learning, right? Because you don't get like a how do you say, just one answer. You get like a range of answers. So remember, what here we are saying is this is just one metric. So the WSSC that we are looking at, it just gives you, okay, this is one metric. So now what you have to do is like, we are going to start with this and say, okay, maybe we can say, what, maybe a number of clusters like between 5 and 10, whatever that values are. And then you have to bring in other metrics to basically see which metrics make sense. Remember the Walmart sales data? Did I have this one? I think I did, right? We'll bring it up. So Walmart publishes data. Yeah, there we go, right? So basically Walmart looked at purchase patterns. And there's a link for this in the slides, right? You can look at this. And they published, these are the categories for us. And I think they came with like 35 or something, something 30. I forgot the exact number. Let's say 35 for the argument's sake, right? And you can see these are the categories they set, right? Now, how is it 35? Why not like 37? Why not 40, right? Because they run the clustering, then they look at the data, right? I mean, because they probably did some manual analysis too, and then say, okay, let's look at the clusters. Meaning, when I say clusters, these are items people purchase together, right? So, for example, right, let's say, let me see. Okay, let's say, actually, let me talk this one. So let's say initially, these two were one category, baby items and milk, right? So let's say, a new parents go into Safeway or Walmart, and then they buy, say, let's say babies and whatever, right? Creams or right, wet wipes. I'm trying to think back a few years back, baby stuff, and then they also buy a gallon of milk. Okay, so when you look at the shopping cart together, now you have diapers and wipes and milk. All right. Can you leave them? Can you does it make sense? Like from your perspective, probably not, right? Because like a lot of people buy a gallon of milk, right? Who doesn't buy baby stuff, right? And vice versa, right? Sometimes people just come to buy let's say you're running out of diapers, just come in to buy diapers, and that's it. You don't bother with the milk. So then what they will do, they will say, okay, you know what, we should separate this. We should separate this cluster even further, right? So remember, and that's what we did. Remember when we did the analysis, right? We did this kind of manually. So here, right, we started with the k equal to, where was that? Yeah, and then we looked at the data, and we said, oh yeah, it doesn't really, so we need to divide further. So we went to k equal 3, right? And this is the process, right? So it's kind of, yeah, so it's and this is what probably Walmart did at a much larger scale. They said, okay, maybe we should separate them out. And then when they look at the new cluster, they say, okay, this makes sense for us, right? Because sometimes people just come into Walmart just to buy a gallon of milk, nothing else. All right. So that's how you have to start thinking about this. Like this WSSC graph only gives you a starting point. Then you have to bring in your other metrics that actually is important to your data to do clustering. And this is going to be different for everybody, right? I mean, depending on your data and your domain, right? What else is important to you? Like for Walmart, right? They wanted to make sure the shopping basket looks not identical, but more or less similar, right? So when they look at the final baskets, then they're kind of all over the place. Then the clustering is not done right. Right. So yeah, does that make sense? Hopefully, it give you sense, right? So always look at K-means as kind of a starting point, and then you have to consider other factors to determine. Yeah. Very good, very good. So how do you visualize the data? So this is good. So you guys are kind of asking the questions leading into the next section. So in this here, right? So I can visualize data very easily because it's two-dimensional. I had two axes, x and y, because right, number of features too. But you can sort of start saying, okay, wait a second, but in real world data, I have more than 2 attributes, right? So for example, here, right? Even though here I just considered MPG and cylinder, right? Maybe, right? What if I want to start adding more data? Yes. So what we need to do is we need to basically bring these dimensions to 2-dimension. We just, right? And that's what the next section is all about. Dimension introduction, right? We'll talk about this. Great questions. Good, guys. Anything else here? Okay, I think that's that. All right. I'm going to zip through the next one very quick, and then we'll look at the next section. So the other one is so this is a really fun lab, figuring out Uber hotspots, right? So I saw this data. Uber published this a while ago. It's part of a Kaggle competition, right? So data is pretty simple. Just timestamp, latitude, longitude, and base number, right? So timestamp, we get it, right? What time the pickup was made, what's the location, GPS coordinates, and base is like the some fencing area, but it doesn't matter, right? I don't care about that. So what I really want to zero in on is like lat and long, because I was trying to understand, can I predict demand, right? So that's what this lab is showing you guys, right? So I have 2 data files you can see, right? One is like 10,000 data points. So this is sort of small data. And then the other one, we about like 500,000 data points. So I'm going to start with like a simple one, 10,000. I download the data. So this code is pretty boilerplate. You will see this in all our notebooks. Basically, what it says, like if you have data locally, use that or just download it, right? That's pretty much it. So it says, yeah, I found the data here. All right. So read the data. Okay. And you can see just 4 columns, right? Daytime, right? So daytime is treating as an object, and that's fine. Again, I'm not looking at daytime into my account, so that's fine. And lat long is float. That's what matters. That's what I care about. Okay, and this is some sample data. Right? You can see, you get it's pretty clean data, right? So, but I'm sort of doing a cleanup anyway, just to be sure. All right. So my vectors are here. What's my x? Because I'm going to group only by lat and longitude. All right. So start with that. Lat and long, right? Again, and you can sort of see the pattern, right? At the end of the day, you figure out your x, meaning, from the original data, what's going to be x. And in this case, we lucked out because, they're all numbers and they're clean. So, I don't know how to do any, any cleanup or, any of the encoding, any of that, right? So I just get my x. That's it. My x is done. Oops. Lat. Oh, that. All right. Yeah. All right. That's my x, right? Just bunch of variables, right? Two columns. And that's it. I'm going to just give it to Kmeans right away. That's it. There's no more to be done. Okay, so Kmeans, I'm saying, okay, let's start with 4 clusters. All right. And right, you can see the Kmeans, exact same code, right? Fit inertia, all that. So for 4 clusters, W like 80. Okay. So let's do a hyperparameter tuning, right? I say, okay, let's do it because I don't know if what the right value of K is, right? So we're going to do like a little loop. So I'm going to say, run from 2 to what is it, 10? Yeah, okay, so let's say 10, right? So I'm varying K by 2 to 10, and then for each K, I'm initializing a new Kmeans with a different K, right? So let's get the loop going, right? And you can see it's very fast, right? So you can see I can see the numbers immediately kind of coming down. Let's kind of put it in a graph so we see it better. There you go, we get it, right? So it's kind of going down, right? So right, so maybe like around like 7 or something, it starts going to taper off. Or somebody could say, oh, maybe 9. Maybe I want to do like a little bit more, right? Maybe you can say instead of 10, how about we do 20, right? Sure, we can do that too, right? But the thing is, you can see how easy it is to kind of experiment, right? That's the part I want you to take away from here, guys. So that's my data frame, plot. There you go. Now you can say maybe, maybe 10 is more, more, right? So it's perfectly up to you guys, right? Again, like I said, there's no right or wrong answer, right? Only thing is we cannot get like a range. So, all right. So let's say, I don't know, let's say I pick 7 or something, right? Because it's kind of bending over here. So I say, let's say I pick 7 clusters. Here you could do 10, right? Nobody could argue with you, right? So I say maybe good clustering would be like around 7 clusters, right? So, okay. So cluster 7, my inertia is like 9 point something. Again, you can see, right? So, it's kind of coming down very quickly and then kind of stabilizing. Okay. So we can, we can do the predictions and all that, right? So again, right? So you can see here, right? So what it does is each trip, each pickup is assigned to a cluster. How many clusters we have? We have 7 clusters, right? So you should see like samples. Let's say, let me do a sample. That's always a good idea anyway. All right. All right, there we go, right? See cluster ID prediction, right? 3, 6, 1, and so on and so forth. So each trip is assigned to one cluster. Remember, K-means is a hard clustering, right? Because, only one. A trip can only belong to one cluster. Okay, good. So, so it's done the clustering, but you can sort of print out the cluster size as well, right? So you can say, right? You can say, okay, what's the biggest cluster? So cluster number, what is it? Cluster number 2, oh, not 2, 1, had a lot of pickups. Remember, these are the number of data points, right? So let me sort this by, easy to, okay. So cluster number 1 had, 4,000 also pickups, followed by cluster number 2, which has 3,000 or some pickups, right? So remember, these are pickup, Uber pickup, and so on and so forth. So not all the clusters are the same. We know that. So there are some busy clusters, right? Some not so busy. But the cool thing is, right? These are GPS coordinates. So we don't have to kind of just squint at the numbers. We can actually like put them in a graph, put them in a map. And that's what I want to go, right? So let me see if this slide is up. Cool. So here, what I've done is I wrote some code to basically print out some JavaScript to visualize the data. So the way I sort of visualize the data, let me show you guys how I done this data, right? So basically you have to copy this whole JavaScript code, right? When you copy this, you have to be careful. Don't miss any brackets or anything, right? So all this is it's like a Google Maps JavaScript code. And you're going to paste it here. I can format it a little bit just to make it right. And then say run, where's my run command? There we go, right? Yep, that's it, right? So this is pretty cool. So what you can see is, right? So the way I have done the visualization is like this. I basically said, I want to, remember K-means all about centers, right? So I'm going to center the data in a GPS coordinate. And then if it has a lot of pickups, I'm going to make a circle bigger, right? You could have done it differently. You could have just said, you could have just put a little pin and then color coded the pins accordingly, like a heat map, right? So you can say, okay, if it's like a, really hot pickup, I'm going to color code this pin to red, and then maybe next one maybe orange, things like that, right? But here I just wanted to draw a circle just to kind of, just to illustrate the size. That's it. So as you can see, the bigger circle, right, that indicates where's the center point, kind of, right? Yeah, Midtown Manhattan. Yeah, sounds about right, right? A lot of Uber pickups there. Followed by this circle, second circle, right? Where is it centered? Again, you look at the center, right? Where it's centered, kind of like in Upper East Side, Central Park. Yeah, right? Makes sense, right? And then followed by this, like, these guys, what is it? This is basically Brooklyn, right? You just get the idea, right? So they're pretty cool, right? So just using K-means, we can sort of, we are doing like a little heat map of Uber pickup locations, right? And we can predict demand, where where the demand is going to be. It's happening. Pretty neat, right? So how many clusters did I say I had? Was it like 6 or 7? How many did I use? 7, right? Yeah, okay, 7 clusters, right? So look at the map. We should see 7 clusters. So 1, 2, 3, 4, right? 4 here, 5, right? JFK Airport. Okay, 5, right? 6, I think this is New York Airport. All right. Yeah. You can see a seventh cluster, and they get smaller and smaller, right? You can see like a 7 red dot. Okay, yeah. So I see one right over here. Right. What's here though? Right. I don't know. Anybody knows New York better than I do? Anyway, apparently there's like a, there's a pickup. This is a hotspot. So I don't know what's here. Like a ferry terminal or something, maybe. Anyway, but you guys get the idea, right? So right. So now I can plot them on the map to see where my hotspots are. Pretty cool, right? So again, just simple K-means, right? And and with real world data, Uber pickup locations, and we are able to predict the demand. And this is very important, right? Because imagine for rideshare companies, like say Uber and Lyft, they want to be able to predict demand very accurately, right? Because so imagine there's like a Friday night or something, right? You are before COVID times, let's say you are at a club, at a restaurant, and you come out of the restaurant, you want to get a ride, you open your Uber app, and then it says wait time is 20 minutes. And then you open the Lyft app, it says wait time 2 minutes. So you should, most likely you will get the Lyft, right? Because the service is pretty much the same, right? Because of wait time. So what's important is once the demand hits, it's too late to respond because there's probably traffic, so you cannot get drivers there fast enough. So you need to predict demand and send drivers there beforehand. Because otherwise, you're kind of losing business to your competition, right? Because people just open apps and then say, oh yeah, 20 minutes was 2 minutes, no brainer, right? I'll choose Lyft. So, and that's why this is important. So you need to be able to predict demand and then send drivers there. And I used to travel a lot for business, and I take a lot of Uber and Lyft, all right, for my work. And I talk to the drivers, and sometimes they will say, like, they will get an alert on their phone saying, hey, there's a surge happening, and if you drive to this location, we will give you like a $50 bonus. Even if they don't pick up any rides, they just want the drivers to be like, go and wait, right? Let's say there's like maybe they figured out like and San Jose Airport is a great example. Like that's my my hometown airport, San Jose Airport. So like Sunday nights, a lot of people come in, right? Like for example, a lot of business trip people, right? If they have like a Monday morning meetings, they will come on Sunday nights, and this is a pretty established pattern, right? So Uber and Lyft, they will kind of they will know this because they can figure out the right request, and they will say, okay, Sunday night, if you drive to San Jose Airport and then just wait in the parking lot, we just give you $50. Because why? Because they are priming, they're getting ready for the surge, right? So anyway, right? So these are things they had to predict very early on and then react rather than reacting. Because once you react, it's too late. Good, guys. So hopefully this gave you pretty good sense. Like again, like I said, right? K-means doesn't have to be boring. So you have some good data. K-means can do, you can get some pretty nice visualizations and all that. All right, guys, let me pause here for a second. Any questions on this one? Did you guys get the map working? I was kind of curious how many people managed to get the Google map happening. Yeah, very cool. Yeah, exactly, right? So yeah, so this is one of the fun labs because you sort of get to see the data, put some JavaScript on Google Map. That's pretty nice, right? So one question I want to ask you guys is this, right? So we're looking at the map. So let's say you come and say, here's your findings, and your largest pickups are like Manhattan Midtown. That makes sense. There's a lot of people live there and work there, right? But look at the JFK Airport. It's not a whole lot, right? Shouldn't we expect a lot of traffic? A lot of pickups at the airport? Why do you guys think airport is not not picking up not that much? Anyone has a guess? Could be time. Yep. No, so yeah, that's pretty. Actually, now it's pretty accurate, right? Yeah, not many people are flying now due to COVID virus. Yeah, that's true. See, kind of what I'm asking is, right? I'm kind of asking you to justify your model, right? Let's say, you came and showed me this graph and say, and I say, look what I found. I'm kind of, trying to trying to make you defend your model to say, is this right? I mean, why are you not seeing a lot of traffic? I'm a lot of pickups at JFK, right? Because yeah, that's good. Yeah, actually, you can make an argument. New York has very good public transit system, so maybe people use public transit at JFK, right, to get to right, get to the location. Yeah, that's plausible explanation. Any other guesses? I'm kind of curious. Um, so those are too good, right? I mean, meaning you can say, I mean, if it's like date is now, but look at the date though, right? Look at the dates here on the data. Where's the date? All right. So date is like 2014. Basically, that's basically the time the data was published. So again, this is not something you would know until you know what was happening. Remember, these are early days for Uber and Lyft, right? So when they were formed, right, and they were kind of getting popular, taxi companies fought them very hard, right? So basically, in the airports, a lot of airports actually did not give them permission to do pickups because they were taxi companies had a very strong hold on the airport, right? So the early days of Uber and Lyft, they just couldn't do a lot of airport pickups because that was pretty much taxi companies. And we know what happened since then, right? Uber and Lyft became so popular, airports have to accommodate them, and taxi companies lost out, right? But so this is 2014, all right? So kind of a semi early days for these guys. So in a lot of airports still kind of ban them, and that's why. I bet if you did the plot now, and imagine there's no, like, let's say not now because now it's kind of COVID. Let's say you did for last year, you would see a big circle around airport, right? Because very popular. But so I mean, and the reason I asked the question is like just right. Remember, you need to be able to understand the data, right? So this is not something Kmeans can tell you. Kmeans doesn't know anything about Uber and Lyft not allowed in the airports. Right? The only thing he can tell you is, look, this is the demand pattern, right? Airports not so much. And it's up to us to go and sort of interpret and say, is this right? Is what it's saying, right? Does it make sense? Yeah. And for that, you need to kind of understand the data, meaning, what happened in the rideshare industry right around this time. Anyhow, so I hope this made sense, right? Again, and this I always tell to everyone, say, look, you can run any machine learning algorithm you guys want, right? But you have to understand the data first. Only then you can really make, good interpretation, right? So good, guys. So that was a cool lab, right? Nice graph, simple, K-means, and then, put them on a graph. Any question on this one, guys? Oh, good question. So the circles overlapping, right? Okay. I'm glad you picked up on this. So the way, again, remember, this is kind of my visualizing idea, right? I kind of wanted to. So the way you got to think about this is like, remember, these clusters have a center. Remember, they have a GPS coordinate, right? So the center. Let's look at the first circle. So the center is. Let me actually draw this here. Let me actually draw here, right? So the way I kind of did this is like. So let's say these are my centers. Let's say this is one center A, right? Change the color. Yeah, another center, actually B. And let's say change another color, another center C. So I could have simply color coded them and then say, right? I mean, if it's hot, C, right? Then B and A, right? So basically the idea is like, you're trying to predict the, a demand location, right? Where the demands are going to be. So right, which location. So what I did was instead kind of I said, what, hey, I want to just visually kind of represent, how the demand is. So I kind of draw a circle. So bigger the circle, sort of the bigger the demand. All right. So where was this? Right. So and then something like this, right? But since this is a very small geo area, right? Because Manhattan is pretty small, right? They are kind of overlapping. So I could have shrunk the circles not to overlap, but then they were like way too small to see. So yeah, so this is just remember, this is just a visualization. That's what's overlapping. The actual data doesn't overlap, right? So there's no points that belong to like this guy and this guy. Remember, K-means points always belong to one cluster. It's just my visualization. So I could just imagine I could just kind of keep shrinking the circles so the circles don't overlap. But then at that point, I tried that, and at the point, it was like they were like dots. It was very very hard to tell them apart. So that's why I did this. So yeah, so here it's just my visualizing also overlapping. You look at the center point, right? Big circle, where is centered? Right here. The next one, where is centered? Like a slightly above here, right? Yeah. So look at it, yeah. And you could come up with like you could maybe come up with like another one that says maybe you're like shading, right? The regions. Like, so you can do like have you seen this heat maps, right? During the election, right? Kind of like that. You could shade like neighborhoods, say where the demand is, like red, orange, and things like that. Yeah, exactly. So what Kmeans tells you is basically where the center is, right? And that's it. Then we're kind of interpreting it after that. Good, guys. Very good. What else? So hopefully that made sense. Again, yeah, right? Yeah. Good question. So it's kind of, yeah, I mean, K-means is kind of similar to, you can make a similar argument K and N, right? But remember, yeah, so, but K and N is basically, it's a supervised, right? So, so K and N kind of uses this, kind of the similar approach, but trains on supervised data. So I'm going to set you guys up, another one. Let me just do this right now, if I forget. ECA. All right, good, guys. So that's K-means. Any question on this one? So we had done 3 labs, right? Kind of progressively, a little harder. Yeah, but K-means, as you can see, is very easy to use. And once you prep the data, it's just just a couple lines of code, right? Which you are seeing this in all of these. That's it. All right, guys, good. So so the homework folder is open, so you can sort of see here, right? I put the link here, class submissions. Where was that? Right. So I was just looking at the so I'm sort of numbering these, right? And then you can see, so we have done about 21 labs. So that's pretty good, right? So if we just kind of kept up with this, 21 labs, that's very good, right? And I just started another one that's for PCA, right? So when you for the next lab. So but right now the K-means submissions are open, right? You can sort of look at these, right? And look at these data. Okay. And again, guys, if you're a little behind, don't worry, just submit, right? Because just just submit the data, submit the lab, because that's what we learn, right? So, all right, guys. Any other questions on K-means? All right, next one, I'm going to talk about dimension reduction, right? So again, so this is again, we done K-means, so please run through the labs, and then I will also upload my solutions to Google Drive as well. So let's look at something a different algorithm. It's called dimension reduction. Okay, so let's see, we have about 30 minutes. Okay, that should be enough. And we'll do some theory, and then I'll also assign the labs for this one as well, right? So, all right, guys, are we going good? Any questions before we go to the next section? Okay, good. So we kind of touched on this, and imagine somebody gave you a pretty large number of columns, right? Someone gave you data that has like way too many columns, right? And in machine learning, we have seen the more data we train on, usually the better, right? But doesn't always mean like doesn't mean always, because sometimes when you have just random columns, they introduce noise than signal, right? And also, as more data you run through the algorithm, more time it takes and all that, right? And it takes more time, more compute power, more memory, and everything. So imagine, right? So here I'm showing like feature 1, feature 2, right? Let's say we have 100 columns. But do we really need 100 columns? Out of the 100, which ones are more important, right? So, and we sort of did something along the lines, remember in random forest, we can, random forest will actually tell me what are the important columns. However, in order for it to do this, it has to go through all 100 columns, right? So at that point, you kind of, you already spend the compute power, right? I mean, you already kind of, send the whole 100 columns to random forest, and maybe it came back with like, hey, out of the 100, these are the top 10 columns. But remember, yes, that's good. It's actually telling you what, what are the top 10 columns are, but it has to evaluate all 100 columns. So you're not saving any compute power, right? So is there any other way of doing this? Right? Can we sort of reduce the number of dimensions? Or, that's what it's called dimension reduction, right? So one thing you can do is, you can say, why don't I just drop the columns? So somebody gave you 100 columns. You say, you know what, I'm going to just drop 90 columns and only pick 10 columns. But how do you pick those 10 columns, right? What if you accidentally drop some important feature? Right? So these are challenges, right? If you want to simplify. So how do we do this? So why do we do this in the first place? Remember, the more columns you have, right, the more computation it takes, right? So you can sort of see, I'm just doing like a thing like, how many, right? If you're trying to do like a combinations, right? So if you only have like, 10 columns, right, there's like 45 combinations, right? And if you're 100 columns, then, like, 4,500 combinations. So just doing it like, selecting, by hand, it's just not going to scale. We need something better, right? And also sometimes when, like, for example, and this is kind of, what you were asking earlier, let's say I have some sensitive data. I don't want to give it the sensitive data, right? And you guys know this, like, for example, let's say, one data is social security, right? When I give it to somebody, I want to mask the data, right? So now my social security number is now encoded into something for, for privacy and sensitivity, right? So rather than giving the original data, I want to kind of give them like some sort of a manipulated data that still has the same signal, but doesn't reveal what the original number was, right? So, and also one of the side effects and is a sort of the side benefits is when you do dimension reduction, it also eliminates duplicate data. For example, if you get like tons of columns, and let's say some of them are duplicate. Let's say you merge some data, and now you have two heights, right? So let's say one department is measuring height in centimeters, and another department is hiring, but measuring the height in feet, right? And same data, but in different format. But it's kind of hard to identify. But when you do dimension reduction, that process will eliminate these duplicates, right? So it's kind of an added side benefit. All right. So how does it work? So the way we work is like this. Let's say this is my original data. Let's say I'm Walmart. I have all this data for my customers. I don't want to give this to to somebody to analyze, right? Because this is sensitive data, and I don't want my data leaking out. So what we do is when you reduce dimensions. So remember, I have like 1, 2, 3, 4, 5, 6 columns, right? So out of the 5, sorry, and let's say customer ID is the same, right? What we do is we are going to create new attributes. I'm calling it ABC with some different, they are different values. And if you look at the data, like, if you compare these two data sets, it's not very obvious where A came from, right? Because A doesn't map to like, online orders. Right? This is not like a one-to-one mapping. They are blended together, right? So what we do is we take all the data, we kind of put them through an algorithm, and the algorithm creates new attributes that has all these things blended in. So it's like, I think like you're kind of making a smoothie, right? So imagine kind of, right? Kind of, let's say, this is like, let's say this is apple, strawberry, banana, right? And when you make a smoothie, you're just putting them all in and blending it together. So you're creating new features, but they have, how do you say, mixed taste, right? It'll taste like a little bit of apple, a little bit of strawberry, a little bit of banana, right? Because they all blended together. So gonna make sense, guys? So dimension reduction, and this is one of the misconceptions I see from a lot of people. People think we're just dropping attributes. No, we're not dropping attributes. We're sort of blending all the attributes and coming up with new data set. right? That has, that's a, thing like a process of making a smoothie, right? You're putting in all the fruits in the blender and then coming up with different attributes. Is that going to make sense, guys, on a very high level, right? This is an important concept to understand. Exactly, yeah. So I see the comment from Vasily. It was like when you do dimension reduction, remember, like these highly correlated features will be blended out. Like for example, right? So let's say let's say this is banana and this is also banana. When you put them in the blender, they just become one, just banana, right? So when you do dimension reduction, it will basically kind of merge them into one column. So does that make sense, guys? This is the first thing we need to understand, right? So dimension reduction doesn't mean we drop the data. We all drop columns. We blend them together and we create completely new columns. Each column has a little bit of data from the previous columns. Like for example, column A, right, might have come from, just to kind of give you a sense, right? Column A might have come from this and this. Column C might have captured data from these three columns, right? But it's not like a one-to-one mapping. Does that make sense? Yeah. So how do we do this, right? So let's kind of look at some theory behind it, but I want to make sure you guys understand what's happening, right? So the kind of the same thing here, right? When you're reducing dimensions, think like you're sending a photo. Let's say you're at a nice beach, right? You see the sunset. You're like, oh yeah, I need to send this picture to my mom, right? Whatever you say, take a picture, right? And send it send a text message. Let's say your original picture is like this dimension, like 1600 by 1200, 2800, and it's pretty large size, 1.6 megabyte. So a lot of the text messaging application, they won't send the actual image. They will actually kind of shrink the image down, right, to save bandwidth, right? So maybe the one actually sent to your mom is basically just say just reduced size, like 300 by 500. But still, you can see the right, even though it's a reduced image, yes, you lost some pixels, but you can still understand what the picture is about, right? Because yeah, so even though we lost some data, the overall signal is still kept. But if you reduce it like so much, like here's another one, right? Here I'm reducing it even further down, like 100 pixel by 170 pixel. But you can sort of see here, right? Now the picture is starting getting distorted. Right? You can sort of see it. I mean, look, compare these two pictures, right? This is still pretty close to the original, right? But this one you can sort of see, things kind of started getting a little fuzzy, right? So anyway, and that's the danger of reducing dimension too much, because if you reduce too much, you end up losing signals. So you kind of want to find the sweet spot. Yes, we are cutting down dimensions, but where do we stop? Does it make sense? Right? Hopefully it made sense. Okay. So again, like I said, not just simply dropping attributes, right? We come up with new variables, right? So, and the goal here is we still want to retain the original signal, right? We are losing some information, that's for sure, right? When think like compressing a picture, right? I mean, yeah, you're definitely losing some, some information, right? Because original picture was 1.6 meg, this is 38 kilobyte. There's no way you can capture everything in 38 kilobytes. What was in 1.6 megabytes, right? You're definitely losing some information, but the idea is still keep as much original signal possible. Yeah. And also, we want this to be very easy to compute, right? Let's say I'm shrinking the picture from here to here. It should be like fairly quick. It doesn't have to be like a very highly complicated, it takes a lot of CPU on the phone kind of a thing. It should be fairly quick, right? And also, another thing we want to dimension reduction is like you don't want it to be reverse engineered, right? Because remember, let's say remember the customer data. Let's say let's say this is my original data, and for my let's say I hired an analytics company, and then I gave them ABC. We don't want them kind of reverse engineering back into what C is like Amex. You know what I mean? Because that defeats the whole purpose. So we want this process to be basically one way and quick. So not easy to reverse engineer. Yeah. So, all right. So now that we understand the basic algorithm, I know what it does is. So let's look at one concrete algorithm that does this called PCA. Right? It stands for Principal Component Analysis. Okay? Let me show you guys what that stands for. So PCA is basically a dimension reduction algorithm, right? You can sort of see here where we are, right? Unsupervised, dimension reduction, PCA, right? Okay, so here's an idea, right? So let's say it's my original data, I had 100 features. I want to sort of bring it down to 10 features. Again, remember, we're not dropping data, right? We're not dropping columns. I want to create 10 new features that kind of captures the essence of the original data, but still, much smaller, right? So it kind of capturing the signals, and you're losing some data, but without losing too much. Okay, so the way we do that is like, kind of, let me just, showing an example, right? So the math behind this is basically, eigenvalues and eigenvectors. We're not going to go too much into this, but I'll give you a quick example. So imagine this data, right? So let's say I'm doing a survey. So I'm asking, okay, what's your age and how much time you spend online? Just two questions, right? So what we have is, so I have two variables, age and how many hours you're on the internet. So there's two variables. So basically, it's a two-dimensional data set. In the vector language, we call them, I have two vectors. Right? Because I ask two questions, right? But then I add another question. Let's say age, how many hours you spend online, and how many hours that is on the phone, right? So now I'm asking three questions, right? So I have, right? So now it's three-dimensional data. So I have three vectors. So you just get the idea, right? So the vectors represent the dimension of the data, right? So imagine you're plotting data, right? It's kind of like, you're plotting x1 and x2. This is two-dimension, right? And if you had another column, maybe three-dimension x3, right? I mean, that's as far as we can visualize, right? More than that, it's impossible for, not impossible, hard for us to visualize. But the math doesn't care, right? Math doesn't care how many dimensions we have. We can, the math is the same, it's just more complex, right? So that's basically how eigenvectors are mapped, meaning how many dimensions is your data. So my vectors equal to my number of dimensions. So if I have 10 questions, I have 10 vectors. Okay. Now, remember your high school math, I guess, right? Linear algebra. When I say vector, what do we mean by vector? Vector has a direction, and also vector has a value, right? Because when I'm drawing a vector, right? I'm drawing a vector, so this is like going left to right, and this is the size. So if I draw two vectors like this, right? Vector 1 and vector 2, you will say, yeah, they're kind of pointing in the same direction, but they're not the same length. And if I draw another vector like this, right? Let's say vector 3, you will say vector 2 and 3 are the same length, but different direction, right? So vectors have direction and length, or we call them value, right? So that's it, right? That's the basic premise behind it. So eigenvectors have a direction and values, right? E vector new value, right? All right, so that's the basics, some basic refresher. So imagine this. So the example I look at this like this. Imagine there's a town which has roads running north to north to south and east to west, right? But there's like an alleyway kind of running like diagonally like this. And let's say most of the restaurants are in this alleyway, right? Now, if you only let's say you're only walking north to south and east to west, you're not seeing a lot of restaurants, right? You're kind of missing out in the ones on the alleyway, right? So you're not seeing, imagine you like doing some window shopping, right? And if you just walk north to south, east to west, your exposure to the number of shops or restaurants is less. To maximize your exposure, you kind of want to walk down the alleyway, right? You want to kind of walk in this diagonal, because then you can get to visit all the shops. So that's the idea behind this eigenvector principle. Meaning, right? So even though we like to think like our axis like this, right? Kind of like x and y like this, right? Sometimes if you just travel in this axis, you will not experience all of the data. Sometimes you can maybe travel like this, right? Like a little slanted. And that's what eigenvectors do. So let me show you guys this. Let's say this is my data, right? I have two axes, x and y, age and internet, right? Remember the data we talked about? Age on the x-axis, hours on the internet on the y-axis. And this is my data looks like. And if I ask you guys to draw a vector that captured most of the data, that's not x or that's not y. That's actually this guy, right? That's kind of, you can sort of see here, that's capturing the large kind of spread of the data. You see that, right? So my data is a triangle. So rather than traveling, because if you go just X, right, you're only capturing just a small amount of data, just this, right? If you go Y, you're capturing a little bit more than X, but again, not as much. But what this guy is doing, he is capturing the most amount of data by going kind of in an angle, right? Is that gonna make sense, guys? And this is the idea behind this. So this is basically called. So I got my first eigenvector, right? So we have to say, okay, draw a line that captures most of the data. You're going to draw like this. Yep. So that's my first eigenvector, right? So hope you guys are with me, right? Then I ask, okay, then I say, you know what? Draw me another eigenvector that's kind of that's building on the previous one and capturing extra data. So remember, you guys already drew this one. We already drew EV1, right? This vector is already drawn. So now I have a choice how to draw my next vector. And remember, I don't want to overlap with the previous vector, right? Because the previous vector already captured some data. So if I don't want any overlap, I have to do it in 90 degrees, perpendicular. You guys understand, right? Think like a math term, right? Imagine, you're drawing two lines, right? And you want to minimize the overlap. So you don't want to draw like this, because now, they're going to capture the same data in different angles. What you want to do is you want to draw like this, orthogonal. Then, there's only there's no overlap. Is that going to make sense, guys? Same principle here. So if I say, okay, come up with a second eigenvector, but don't overlap with the previous one, I'm drawing another one, which is 90-degree angle. Yeah. Now, challenge for you guys. What if I ask you to draw like a third vector? Let's say EV3. And I'm saying, all right, guys, draw another vector, but your conditions are it cannot overlap with EV1 or EV2. How will your third vector look like? Can you guys tell me in the chat window? If we ask you to come up with a third vector with no overlap with the previous two, what would you do? That's right. That's right. So it's like, you're doing it kind of exactly, kind of coming out of the screen, right? Can you imagine, right? Because you already drew two-dimensional vectors, orthogonal to each other. So your third vector, you cannot draw like this. Because, then, if you do this, you're going to have an overlap. Exactly, right? So now what you're doing is you're kind of, right? So don't do that. So let me delete that, right? So now what you need to do, you're kind of, imagine this vector is coming out of the screen towards you. Because then it has no overlap between these two guys. Does that make sense, guys? Right? So what you're doing is you're trying to draw lines that capture data, but without overlapping with your previous vectors. So basically what that means is each vector is going to be orthogonal to each other. So we can kind of envision three-dimensional. I can kind of imagine, okay, three-dimensional data, right? Beyond that, I cannot visualize. And so, but no big deal. That's where the math comes in, right? So is that kind of make sense, guys? Kind of the basic idea of eigenvectors. Eigenvectors is basically your original data. You are trying to create vectors, right? Think of them as like new axis, right? That captures the original data, right? Captures most of the original data, right? So we started with just one. So it kind of captured like in this direction. And I say, okay, I'm going to add another vector that's going to capture the what's left. Then I sort of drew like this. So within these two guys, we have a pretty good capture, right? One went through like in this high, right? In this plane, other one is like a perpendicular plane capturing this. So that's where the math is, right? So basically, given any vectors, right? So because at the end of the day, x and y are vectors, right? Just imagine these are right in computer science and machine learning, we work on vectors. So I given you two original vectors, x and y, and you're going to come with a different set of vectors that captures most of the data without losing too much definition. And this process is called eigenvectoring, right? So, and that's what it is. So now what I'm doing is, right? So now I can actually capture this data along different axes. So now I have two different axes, eigenvector 1, eigenvector 2, right? And they try to capture as much data as possible, right? So the thing you remember is the data hasn't changed. the same data. It's just like we're gonna rotate in the axis a little bit. It's gonna make sense, right? So now we have two vectors, right? EV1 and EV2, right? And this is a process, right? So given a vector, right, we calculate what we call eigenvectors that capture the original data. Okay. So let's kind of put it back into like a kind of concrete. Now that we understand the theory behind this, right? We kind of see how the vectors are computed. Again, this you can look at go read up on eigenvectors and how they're computed, right? Right. It's sort of the, I don't know if you did like probably when would you do eigenvectors? Probably advanced math, like if you did like advanced math in high school, probably like, or some at what do you call here? We call them I forgot the name. Anyway, it's like advanced placement, right? then you probably have encounter eigenvectors calculation, right? So, but pretty straightforward, right? It's just a vector manipulation. Anyhow, so imagine this question, right? So let's say I ask 15 questions. So I'm doing a survey, I ask 15 questions, right? So that means 15 dimensions, right? So my original data has 15 vectors. Okay. Now, let's say, right, each vector, I'm sort of shifting them into different, I'm counting the eigenvectors, right? Different eigenvectors, right? So the first one captures 25% of the original data, just for argument's sake, right? So the first one, remember, I had 15 questions, right? And I calculated my eigenvector. The first one captured 25% of my original data. Okay, that's not bad, right? But if I add a second one, that captures another 22% of the data. So together, what is it? Together, what is 47? So together, I can capture 47% of the original data. Now, why can I add them up? Because remember, they don't overlap, remember? Because they're additive, right? Because, there's no overlap between EV1 and EV2. Just the way the eigenvectors are calculated, they are orthogonal, right? So the information they capture, you can add them up. If they were like this, kind of like, right? If you kind of like, if they're kind of, overlapping, right? If they're kind of like this, then you can add them up, right? Because, there's overlapping data between these two axes. But since they are orthogonal, they are, there's no data in common, you can simply add up their coverage, right? So first one gives you 20% coverage, second one gives you 22% coverage. So together, they give us 47. And I threw in a third one. Let's say that that covers 50% of the original data. So what is it like? If you do the math, 60, 62, is that right? So we add the third one, we have 62% coverage. And we can simply add them up, right? Because the way the vectors are calculated. And if we include the fourth one, so when I include everyone, like imagine I'm sort of adding new axis, right? Kind of imagine like new axis, right? So with fourth one, 62, 13, what is it? 75. There we go, cool, right? So by adding four eigenvectors, I'm able to capture 75% of the original data. That's not bad at all, right? So I basically came from 15 dimensions to just 4 dimensions, right? Because why 4? 1, 2, 3, 4, right? 4 dimension, that gives me 75% of the original coverage. That's very good, right? So if you say that's enough, that's good. Then all we need is 4 vectors. But what if you say, no, that's not enough, we need a little bit more. Then you add the other one, 8, right? 8 plus 75, how much does it cover? 80, 83, right? So we add this, 83% coverage. So maybe just adding by 5 variables, 5 vectors, we're able to cover, 83% of the original data. So where do you stop, right? I mean, and one thing you would have noticed is like, as we keep adding more and more vectors, the information captured is less and less and less. It's kind of a diminishing return, right? So each vector, the first vector captures the most information, right? And that's a challenge, right? When you draw the first vector, right? Drawing the first vector is like capture as much as information possible. When you draw the second vector, it's going to capture less than the first vector, right? Because the first vector kind of already captured as much information as it can. So second one is going perpendicular, and it's going to capture little less than first one. The third one even less, right? So it's a kind of a diminishing returns, right? You kind of imagine like you're kind of drawing adding vectors, right? kind of like we had a kind of picture like this, right? As you add vectors, let's speak loud. Wait, 1 second. Let me show you this, right? Kind of like this. Right? Kind of like each vector, the first vector captures most, the second one's less, right? Less. Kind of like a dimension return. So these are called principal components, PCs. Right? So remember, we started with 15 dimensions earlier. That's the original data, right? And then when I break it down into principal components, just with 4 principal components, right? 1, right? 1, 2, 3. That gave us 70%, 75 or something, right? 75% coverage. Pretty cool, right? So again, how was this calculated? Basically, just using eigenvector mathematics. All right, let me show you this example, and it'll kind of make sense. Right, there you go. So when you're doing the principal components, right? Here's the coverage. So the first principal component captured 60% of the data. The second one captured 20. Right? Look at the right, around 23% of the data. And as you can see, right, every subsequent one is capturing less and lesser data. And as you can see, it's kind of like Kmeans, right? Kind of comes down pretty sharply. And as you keep going, each subsequent vector captures less and lesser data. But let's say you turn this plot on its head, right? So let's say we're adding it up, right? So first one, if we just include first one, that gave me 60% coverage. All right, good. Now we have the second one, and I can add them up, right? So I get 60%. When adding second one is like 20 or maybe 30% now, 20 some percent, right? And they add up, right? Because why? So this is 1, this is 2. Why I can add them? Because there's no overlap. Remember, that's a core principle of eigenvalue. I can keep adding them. So between 1 and 2, I get what is it, like, pretty close, like 90% coverage. If I add 3, right? You can see here, right? If I add 3, again, that adds up. But now you can see as we add more and more, the increment is pretty small. The biggest jump comes from the first vector. Then second vector gives you sort of second biggest improvement, and right. So every subsequent vector you add, your improvement is going to be diminishing, right? So if you keep adding your vectors, you'll eventually get 100% coverage. 1, right? 1 is 100%. But that's not the point, right? Because remember, let's say you have 15 original dimension, right? And then you did the PCA, right? And then PCA gave you another 15 vectors. There's no point, right? I mean, why go from 15 to 15? I mean, then you could have just used the same 15, right? So if we keep adding principal components, you will eventually get to 100%. But the goal is not to go from 15 to 15. Maybe I want to go from 15 to maybe 5, right? And let's say this 5 gives me, like, say, 90% coverage of the original data. So instead of using 15 columns, I could just use this new 5 columns that PCA created and still analyze 90% of my data. Is that going to make sense, guys? Right? So how many do you need? Like, from 15 original, do you need like 5? Do you need like 6? Do you need 7? Only you can determine. You will say, what? Yeah, we need 90% coverage. Sure. Then and adding 5, including 5 PCA components, give you 90% coverage. That's it. Then all we need is 5. But let's say, hey, we need at least 93% coverage, right? Maybe you'd add like 1 more, right? So now 6 PCA components, 90%. Right? So again, you can play around with this one, and you can choose as many components as you want to give you as much coverage as you want. So is this graph kind of make sense, guys? Right? Right? If you look at each component, they can they're Kmeans, right? They're kind of declining. But when you add them together, right, they're additive, right? You can add them, because they don't overlap. Then the graph kind of starts climbing and then kind of works towards 1. So I'll kind of stop here for a second and then kind of see if you guys have any question. And this is called scree plot, by the way, right? This is called when you do principal component analysis, this is called scree plot. That tells you how principal components are behaving. Does that make sense on a high level? So what are the principal components? Calculated using eigenvectors, right? And we understand the concept, but the math is right. Again, you can go pick up any sort of advanced calculus or linear algebra textbook, and they will show you how eigenvectors are calculated. But that's the theory behind it. But we understand the principles, right? We understand what's going on. Any question, guys, on this one?
Hello. Do you hear me?
Yes, go ahead. Please.
Yes. You remember earlier in the course we had the other kind of transformations of transforming the data into higher dimensions. Can we use something, it's a stupid question probably, can you use something like this kind of transformation to also be able to transform, say, the eigenvectors to actually represent even higher dimensions than the ones they have, so we can somehow say, imagine all these features. We get an example, say, of 3 dimensions points, on the plane. If you go, say, by the lines, you can capture, say, somehow kind of as many points as you can on a 3D plot. But if you can, say, try to transform them and have vectors that they are representing, say, shapes like a circle or a sphere or a cylinder, imagine,
Yep.
you can capture even more. So I was just thinking if we have the ability also to mathematically simulate these vectors, the eigenvectors, to simulate hyper, I could say, schemes.
Like a different shapes kind of thing, yeah, right?
Yeah.
Like, okay, yeah, I can see what you're asking. I need to look this, great question. I need to look this up because eigenvectors, the default implementation is, perpendicular, because the idea is, right, you want them to be additive and not overlapping, right? So that gives you the orthogonal value. I'm trying to think. So the way you would accomplish this here, again, I'm not saying it doesn't exist, but, just kind of knowing what we know, the way we would do that is basically by combining enough eigenvectors, you can still accomplish what you want. It just, they're going to be orthogonal, right? Because the reason they're orthogonal is like, they want to capture the data that's missed or the not captured by the previous vector, right? Kind of like, right? For example, so the first vector captures most of the data, right? Because, because that's how we, the vectors are calculated. But, it's only capturing 60% of the data. The next vector is going to capture what's left, right? So, and then, and it captures, let's say, 20 or 25%, right? So just by the mathematics of this, these, and that's what, they are orthogonal. Like, mathematically, like think like, we can imagine this on 3 dimension, up to 3 dimension. Beyond that, we cannot. Yes. But I'm imagining, right? Again, I'm not saying, yes or no. I'm imagining by combining enough of these vectors, you can control how much information you want to capture. Yeah. So, and again, people ask me, so how many principal components do I need? Right? Like it's kind of like K-means. Remember in K-means, nobody can tell you the right K. So if you say, okay, I have 15 original values, okay, should I use 5 or should I use 6? Only you can know, right? Because, for example, let's say 5 principal components give you 90% coverage, right? And using this for your analytics, you get pretty good accuracy. Then you're good. But let's say your algorithms are not working very well. You say, yeah, we need more coverage. Then you keep adding more principal component. But the goal is, right, not to kind of, find the sweet spot, right? Because, if you're using all 15, then, you might as well just go back to original data, right? There's no point in doing a principal component anymore.
Yeah, so I understand it. I understand this way.
Yeah. So I cannot get your question. Again, I haven't seen it personally. Like if you can you do like non-orthogonal vectors? I need to do some research, to kind of, see if it's even possible. Yeah. So
for example, what I would think, for example, say you have, say 3 features that are actually giving a strong, predictional ability.
Yep.
I could probably say transform them.
Let me see if we have an example. Yeah, go on.
Transforming and combining them into one vector.
Yep.
But in order to have, say, a less amount of features,
Right.
I was just thinking if we could just do that.
Gotcha. Yeah, let me see. Samples. Sorry, I was going to show an example. Give me 1 second. I just saw this last night. I was going to show an example. Let's see.
This is, I think, this kind of reduction works in well understood features.
Yep, exactly.
Yeah?
Yep.
I haven't done any work for this week on this Kmeans. I was still working on the previous thing, trying to transform, say, text data into somehow kind of categorical data or vectors or whatever else I could do. And over there, for example, one feature transformed it into 1600 features.
Right.
You have to find out which one of these 1600 features have got significance or not.
Right. Gotcha. Yeah. Give me 1 second.
And then probably you have to just say, okay, I don't need the 1600 features. I need only these 20 or 10.
Yeah. Give me 1 second. Actually, I was going to show you like an example I just ran into yesterday. Let me see if I can find it real quick. Okay. Oh, sorry guys. I want to wrap this up in about next 10 minutes. Give me 1 moment. News groups. All right. There we go. I think this one had. There we go. Okay, cool. So let me show you guys. Okay, so now we understand the theory behind principal component. I want to show you guys how we apply this in practice. Okay. So what we are going to do again. So we discussed this. How many principal components do we use? Again, there's no right or wrong answer. Right. This depends on your coverage. Right. So we can use a scree plot. So scree plot kind of gives you like right. You can immediately gauge how much each of them are covering together. Then you can say right. If how much coverage do we need? But how do we determine? Let me show you guys an example and I'll come back to this, right? So kind of the way you'll think about this. So let's say somebody gave you a data set with 100 features. Now, you don't want to add all 100 features because that just makes the model insanely complex. So let's say I'm doing a PCA, right? So from 100 features, I'm reducing into 10 components, right? Just to give you an example, right? So imagine what the data looks like. Like I have imagine I have data like this, right? So let's say I have initial data A1, A2, right, A3, like we have 100 columns. Now I have 10 columns, right? So let's say B1, B2, B3, whatever, right? 10 columns. Now let's say I am running a supervised learning, right? I'm running on my SVM or random for this we know how to do, right? So I'm let's say there's an X and Y, right? There's like a Y predictor, right? So for my inputs, this is my output. So let's say I'm running a supervised learning, and I'm doing a score. So let's say initially I get like 60%. Now you guys know how to do this very well, right? This is what we spent the last few weeks doing. I given a data, run SVM, random forest. Any supervised algorithm, you guys know how to do cross validation, you guys know how to do the scoring, all this stuff, right? So let's say you do all that and then you only achieve 60%. Okay, so we say, so we say, okay, you know what? Just using 10 components, we are not getting enough accuracy. So maybe we need, instead of 10, maybe we need 20, 20, right? No, let's say go for 50. So original 100 attributes, we do a PCA, reduce it down to 15 components, then do SVM, right? And this time you get 78% accuracy, let's say, right? And let's say you say, we want a little bit more. So let's say from 15, you go to 20 components, right? Do the SVM again. And let's say this gives you say 83% accuracy. And let's say that's acceptable to you guys. Let's say you are looking for minimum 80% and you're like, what, that's good. So that's your number, right? So you can say, original data, 100 columns, and we PCA it into 20 columns. We minimize the data into 20 columns, and that gives us 83% accuracy, and that's good enough for us. So do you sort of see how you make the decision, right? So there's no like an abstract formula you plug in and say, okay, I'm going from 100 to like 17, right? Nobody can tell you this. So it's an iterative process, right? You do some minimization, right? Then most of the time what people will do is people will actually run other supervised algorithm on the reduced data, right? And the beauty of supervised learning is we can evaluate, right? And we can score it. Because supervised learning have a score, right? Which this is what we have done with cross validation and everything else, right? And then sort of iterative process, right? Oh, question was test data. So everything's reduced, including your trained data and test data, right? Does that make sense? You're kind of, right? It's like imagine like somebody's giving an Excel spreadsheet. This is the original spreadsheet. You're kind of coming with another spreadsheet with as much information as possible. And then here, you split, in this data, you split train and test, you do the whole thing. Train, test, split, all that stuff, right? You guys know how to do that. Yeah, good question. So everything get reduced first. Then we do the train, test, split, and do the cross validation, the whole deal. So a lot of the time, so we can sort of think about this in the whole workflow, right? It's an iterative workflow because nobody just does PCA just for the sake of doing PCA, right? Because what's the point then, right? It's like, you know what I mean? It's kind of like, the data has to be processed somehow. So the PCA is an effective way to cut down the number of dimensions, so your algorithms can train quicker, and you can right, you can come up with like algorithm that are easy to interpret and so on and so forth. So they're gonna give you a sense, guys, like a big picture, right? I hope, right? So a lot of the times, and this is an example I want to show you guys, is here's another example. Where was that? Right. So here's the, I was kind of researching this yesterday and I ran into this and I thought this is pretty good. So anyway, so this is basically topic modeling, right? Meaning there's some text data. They're trying to figure out what are the topics mentioned in the text. Topic could be something like weather, could be, right? Could be news, could be business, right? Finance topics, right? So this person is doing this again. I'll put this link. You can look at this here. I'll put this link here, right? This is an example of using PCA, right? So okay, so so here he's doing a transformation and he's putting out the shape. So how many columns are in this vector, guys? Can somebody tell me? How many columns in this vector?
The second number.
That's right. Remember how shape works? Oops. Shape is like rows and columns. So this is text data, remember? So in text data, we have, each word is its own dimension. Remember, this is what you guys did in naive Bayes. So now I have 73,000 columns. That's just insane amount of data. Like I can visualize it, I have no way of right? It's kind of so much data. So then what he's doing is he's doing a PCA, right? How's PCA, right? He's basically just reducing them down to just two components, right? So 73,000 columns are distilled into just two components. So if you're wondering why is he doing two components, because he wants to plot. He wants to plot the data to understand what the data looks like. You guys sort of see this, right? And the plot is, we kind of do work in two-dimensional plot, right? So this is kind of the plot of, 73,000 columns are kind of somehow filtered into just two axes. And there's like a third dimension here to, do some color coding, right? That's what the color coding is. But if you look at this, do you see clustering? Yes, right? So these are similar topics you can see clustering together, right? So let's say this, I'm just making this up. Let's say this is weather information, right? So that's, all the weather kind of clustering together. And let's say, and I don't know, something like, on this side, this is like finance. So even I reduce like 73,000 into like, just two dimension, right? I can still extract a lot of meaningful data. Is that gonna make sense, guys, right? So a lot of the times when you have high dimensional data, and let's say I want to quickly do the plot. So let's say I give you 10 dimensional data and I say, can you plot this data? We cannot see it, right? Because 10 dimension, our brains don't work in the dimension. But you can do a quick PCA. You can reduce 10 dimension into say 2 dimensions, right? There you go. That's it, right? Just say PCA, number of components 2. That's it. That's all the algorithm is. And then it's going to give you an X and Y, and then you plot that. Does that make sense? So a lot of the times when you're high, and this is what you was asking earlier, when you're high dimensional data, just do PCA. Because remember, when you're doing PCA, you're not throwing away, you're not dropping columns. That's very important to understand, right? You are creating new vectors or new components that kind of resembles the old, old component. Thing like making a smoothie, right? You're like, let's say you have 10 fruits, but you're making like, just, one smoothie, right? That has all the attributes of 10 fruits. Now the smoothie is a blend of all the fruits, right? So it's not like no fruit can dominate, but that fruit's flavor is going to be in the smoothie. Is that going to make sense, guys? That's what you're thinking about PCA. Okay, let me see. Okay, let me show
now,
you PCA.
the
Yeah,
question
go on.
here.
Yep.
Done. Imagine now these 70,000 features have become 2 features.
Yep.
We have to have a way to explain what the hell was that all about and what that means.
See, that's the thing of PCA, right? So yeah, go on. Yeah, I know what you're asking, but go on, finish the question.
Well, imagine now why 2 and what is the difference between one from the other? What is the combination 0 and combination 1 means? If we cannot explain that, then I think we're talking about miracles and nobody will believe us.
Right. So when you do that, so your question is like, okay, how do we come to 2? Like, what's the makeup of these 2 components, right? Basically, right? So the PCA algorithm will give you a matrix, right? It'll go something like this. When you do the PCA component, it'll say something like, I'll just make this up, right? Let's see if I have the diagram here. I thought I did. Give me one second. Give me one moment. Okay, we did that. All right. So actually, let me draw like this one. Okay. So you had I'll just do 3, A, B, C, D, E, just 5 components, right? Let's say we are reducing into like 3 components, X, Y, and Z, right? It's X and Y. Keep it simple. Okay. So I'm coming from 5 to 2. Now, when we do this, the PCA will actually give you a matrix, kind of like this. It'll say X is made up of, let's say, actually, let me do this like this: A, B, C, D, right? And so it'll come back and say X is probably made of like, it'll say something like 50% A, right? 30% B, right? Maybe 2% C, and then whatever, right? 10% D, something like this, and then whatever's left, right? And Y is made up of, let's say C is dominant Y. Y is made up of like, say 70% of C, 10% of, you get the idea, right? Something like that. All these numbers should add up to 100. So I'm not doing the math right now, but you guys get the idea, right? So the mix, right?
Okay.
When you do PCA, you can know the mix.
Okay.
Yeah,
Having that, at least you can try to explain something to yourself.
Exactly, right? So
before
you can
try to explain this to somebody else.
Yep, exactly. Now, only this mix, right? For example, let's say I have the data. Person 1 has the data, right? And I am doing this thing in PCA, and then let's say person 2, I only give X and Y. They cannot reverse engineer because they don't know this mix, right? It's like remember, it's like I'm running a restaurant, right? And I'm creating a franchise, so I'm giving all my franchisees my secret sauce, right? They cannot reverse engineer what the original ingredients are, right? Only I know, right? Because I created the secret sauce. Does that make sense, right? So for the others, they are simply using what's the data is given to them, right? For example, let's say they're making a hamburger or whatever, right? And they're applying your secret sauce. They just know how to apply the secret sauce. That's it. They don't know what's in it, right? they may guess, they may say, oh, the secret sauce has some, I don't know, some paprika or some, something else, but they will not know the mix. Does that make sense? Yeah. So PCA, you're thinking about, like, remember, you're blending it all in, right? So think like a fruit, fruit juice or fruit smoothie, right? So only you know the mix. When you create the PCA, when you do the transformation in PCA, you can get this this matrix, right? And then that'll explain what the mix of, how each component contributed.
So now another question, because I have not so much experience, I can say. You use this, say, to create a model. Yeah.
Yeah, we actually use X and Y to create the model. Yep. Mm-hmm.
Yes.
Yep.
Now, if you try, say, to upload the model somewhere, do you use the output of this only?
Right. Exactly. Your model can be only evaluated, right, on the data it's trained on, right? Exactly.
Yeah,
yep.
Yeah.
So whenever you want to evaluate the model, let's say somebody give you original data, first you have to do PCA, right? Create X and Y. Only then the model can support it. Because your model has no idea about ABCD, right? It only knows X and Y. Yep.
Right.
So it's complete. So it's like a complete firewall, right? The model has no idea of the original data. So any testing you want to do, first thing you have to do is you have to do a PCA from here to here and only feed to the model.
Right. So the testing also should include the same transformation.
Yep. Sure.
Right.
Yeah.
Okay.
Okay. So the way, yeah, exactly. So always kind of thing. So I'll kind of stop this. I know we are way over the time. Sorry about that. So the way we will do this, like this, right? Let me go back. Yeah, like this. So, right. So kind of, right. So go to the original data, do PCA, run your supervised algorithm, write a score, and then repeat, right? And then you sort of figure out the number of PCA components you need based on the score you need. So let's say you are aiming for 90% coverage, 90% score. So you need to kind of do the iterative process to find out, okay, to achieve 90% score, you need 15 principal components, and that's it. And then you fix on that. Yeah. Good, guys. Right. So you guys have the slide already. So go. I sort of skipped some slides in the interest of time. I'll upload the lab by tomorrow. Right. Go through the slide, kind of understand, and if you really want to understand the math, right, pick up any textbook, and they will kind of walk you through how the principal components are calculated. Again, there's a lot of math behind it, but again, for our purpose, we want to understand the concept, right? So in scikit-learn, PCA is dead simple, just one line. Remember, so here's the code I was showing you, right? So here, I'm creating PCA, number of components 2, and PCA.fit X, right? And then this, 73,000 columns are magically reduced to just 2 principal components. Why 2? Why PC1 and PC2? Because remember, only 2 components. If I said 3, I would have had PC1, 2, 3. That's it, right? Just a couple of lines of code to calculate principal components. Pretty cool, huh? And then this is what I really like, because even though he reduced it into 2 dimension, and remember this is topics, right? Imagine you're reading like Google News and you're trying to understand what are the topics. The topics you can still see clustering pretty well, right? So they tend to cluster, like, and say, oh yeah, this must be. Now remember, it doesn't tell you what topic that is, right? I'm only saying, okay, I see like, purple topic, whatever that is, we don't know, right? I see like a green topic, and there are sometimes there are overlap, right? For example, let's say the green topic is I don't know, like stock market, and then there's let's say there's a purple topic is, let's say, politics, right? There are maybe there's like interlap, right? Maybe there are some news stories that are stock market and also about politics. But it's kind of, but remember, this is unsupervised learning, right? Unsupervised learning, there's no labels. You can only highlight the clusters, right? To understand what this cluster is, we have to go and actually do further analysis. But the unsupervised algorithm like PCA can only give you, okay, hey, I see a cluster here, I see a cluster here, right? It doesn't tell you what that cluster is. Very important to understand, right? So it will not tell you this is politics. It just will say, I see like different data. Yeah. So anyway, so just again, right, because sometimes when you do PCA, it seems very abstract. It's like, hey, yes, I'm kind of, reducing the dimension. Like, what does it really mean, right? A lot of the times you will see PCA, people using PCA just for a very simple purpose of doing a graph. Right, because you're like very high dimensional data, right, like this. Just want to visualize, you want to get an idea of what the data looks like. So obviously, you cannot draw, you cannot plot 73,000 dimensions, right? So a lot of the time you will see people doing like PCA, because PCA is so simple. I mean, as in simple as in like the implementation is very simple, right? So you can say, hey, let me just do an X and Y real quick. I want to see what the data looks like. Anyhow, yeah, so a lot of the time you will see examples, when you do PCA, and you're wondering, why are they doing PCA before the graph? Because they're basically reducing the number of dimensions to basically 2 dimensions, so we can plot, right? And then most of the time they will also add a color coding. I think, let me see what the color coding here was. Hue. Okay, yeah. So this is like the target. Target name is, so target is basically like a sort of like the topic, right? Sort of the like the business, politics, right? So and that makes sense, right? Because you can sort of see similar stories clustering together. Anyhow, all right, guys. So I'll stop here. I know, sorry, we are very over the time. So, but I hope you guys understand principal component. I will upload the lab say by tomorrow, and please read the slide also. And then this is the I think this is the second to last component. The next algorithm is going to be recommendations. So good. So we are almost there. All right, guys, look at the algorithm map, right? Again, kind of in a big picture where we are. I'll end with this, right? So PCA, right? And then next one we'll do recommendation, and that's it, right? That'll bring it to the end. Cool. All right, guys. So thank you. Keep an eye on the Slack. I will upload the labs, and then we'll see you guys next week. Yeah. Thank you, guys.
Thank you.
Thank you very much.
Thank you.